It's our 13th lecture of Principal Methods and Applications of Nuclear Tracks, and in this lecture we are going to discuss about Low Temperature Thermochronology course. This is about the fission track dating. We already discussed about the fission tracks in our previous lectures. Along with we will discuss the fission track dating. Now in this course we will briefly discuss about the fission track dating. It's basically the low temperature thermochronology course. Okay, so let's start. So this is basically the motivation, time of events, rate of processes, and temperature time history. Okay, so these are basically the motivations. Now move on towards the goal. During our this class, we are going to learn deeply about the understanding of fission track dating. Means what is fission tracks? We will discuss about the count fission tracks. Okay. Once we discuss about the fission track dating, then definitely we have to count the fission tracks. So in count fission tracks, we are going to discuss about this. And thirdly, our goal is using fission tracks length. We will also discuss about the track lengths. Okay. And lastly, we will discuss about the forward and inverse modeling of TT histories. Okay. So this is the modeling. We will also discuss about this in this course. Okay. Move on towards the roadmap. This is the roadmap which we are going to follow in this course. First of all, we are briefly discuss about the background, historical background of this fission tracks dating. Then we will move on towards the fission track formation, how fission tracks formed. Okay, we are going move towards the fission tracks dating methods. What are the methods of fission tracks dating? And then we will move on towards the preparation of samples grains. How can we prepare make these samples? And the important but not the least is basically the age equations we are going to discuss in this course. And then we are going to move on towards the fission track, which is annealing, and fission track length, and we are going towards the annealing kinetics. And lastly, we are going to discuss our modeling, as I mentioned before, modeling of TT histories. Okay, so this is basically the historic background, the starting of our course with the historic background. So for this, I have to mention that two scientists, Price and Waller, in 1962 basically found the spontaneous tracks in natural micas and includes fission tracks by fission of uranium. Okay, they proposed that counting both yields the age of the mineral. So these are the two scientists who basically found in 1962 the tracks in natural mica and the induced fission tracks of uranium. Then they proposed their count rates of the age of any material. Okay, you can say the age of the mineral. Then other two scientists also applied the method to a variety of minerals. Okay, and then they also produced the reproducibility of FTH between labs users, and irradiation was bad. And also to overcome these methodological problems, Howard and Green, the two other scientists, suggest to relate the FTH of the reference age of age standards. Okay, they use age standards. And currently two methods are used for external detector method, and the same scientist Herford and Green in 1972, and the laser based fission track methods also being used, okay, by these two scientists. Okay, very important, which is the laser based fission tracks. Okay, methods, you can see like this. Okay, so now move on towards the next, which is basically the uranium decay. As you know that uranium 238 isotope is basically the unstable in nature. Only fission reaction takes place once your uranium 238 nuclei, okay, with uranium 235, though your fission reaction not going to place. Okay, so to fission reaction uranium 238, okay, is in use. So it's basically unstable in nature and it decays in two different ways. As you can see, this is your uranium 238, which is unstable in nature. This is PT stands for the parent nuclei, and this D 1T and D2T stands for the daughter. Okay, your parent converts into daughter. As you can see, it decays into D1 and D2 means two daughter. D1T, which is this small fraction, means fission is small, and which is lambda 1 and track, and the lambda 2 track, as you can say, which is large, a large concentration, and this is basically alpha decay. Alpha decay is basically the direct decay of the uranium 238, and this fission takes place very a little bit. Okay, so that's why how your uranium 238 decays in two different ways. Alpha decay, which is the ejection, which is the direct decay, okay, spells of a helium particle, and there is a fission decay in which you can see that there is a small contribution, and in this the half-life is basically 4.5 into 10 raised to power 9 years. So that's all how your how your uranium decays in two different ways. Okay, now move on towards next. Our second, as I told you, the one method is basically the alpha decay, which is alpha ejection, you can say, and the half-life is 4.5 into 10 to the power 9 years, while you're also uranium decay with fission, and one in every, you can say that 22 lakhs, okay, 20 lakhs decay. So this only gonna happen in one of the 20 lakhs. Okay, you can say that the 20 lakhs decay, only one there is a chance probability that the fission reaction, that your uranium decay into the fission reaction. Okay, and your nucleus splits and leaves damage trails, and your uranium 238, and in this scenario is the half-life is 1.3 into 10 raised to power 16 years, more half-life than this parent, this daughter. Okay, so now move on towards the spontaneous fission of uranium 238. As I told you that this is the phase structure of uranium 238. As you can say, parent converts into daughter. Okay, and here you can say see that the uranium 238 92 decays. Okay, with photon HV low photon, you can see have a energy of 70 mega electron volts, and it also converts into LT, which is the 100 mega electron volts with an emission of fast neutrons. Okay, fast neutrons. So fission release, you know that fission reaction always releases the energy in range of 200 mega electron volts. So that's why the fission energy here release is basically the 210 mega electron volts, of which 170 mega electron volts are basically kinetic energy. Basically, the kinetic energy of the particle is more 170 mega electron volt. In that, the fission releases the energy of total of 210 mega electron volt. Okay, and fission tracks basically equals to linear damage of mineral lattice along the trajectories of the fission fragments. Now here you can see this is the track formation, how tracks form. This is just a simple and mind-blowing illustration of just for the understanding of the track formation. You can see how tracks formed, different lattices, atoms attached to others. Okay, how compact these formations are. Just to visualize you for the understanding of how tracks formed. Okay, so once your track is formed and some is coming into your tracks, okay, so this is how it looks like your track now deformed. Okay, once this is coming, okay, so here you can see how it deforms the whole track. Now, as we're discussing about the track formation, so after ion exploration spike model, so we are going to discuss the spike model. We already let you know that once your atom is coming, it disturbs the lattices and it forms a track. And once the track formed, all the electrons now move towards the higher band, higher energy level, and as the electron goes to higher, leaving behind the holes. As the holes formed near the track, because or majority is the positively charged holes, we know that the positively charged repels each other, so now holes are repelling each other, so you can say here the vacancy formed near the track. Now the track are now being permanent. Okay, you can see ionization, Coulomb exploration, and relaxation. Okay, so this is basically the rapid massively positive charged particles strips means move lattice electron along its trajectory, leaving an array of positively ionized lattice atom. Positively ionized atom made here, and due to the large amount of positively ioned atoms, they repel each other and make a vacancy. Okay, resulting positive ions dissipate due to the like charges repulsion, as I mentioned before, and thus it create vacancies of for new atoms. Okay, so that's stressed region released elastically strained surrounding undamaged lattice. So due to the vacancy generated, so the stressed region relaxes the elastic strain surrounding the undamaged lattice. So this form is called as the relaxation. Now here you can see the visualization how tracks form. This is a 15 nanometer track. You can see image. So this is how you can see track formed. This is figure atomic scale image of latent unaged tract. Okay, an induced track in Durango Fluorescence observed sub-parallel to its length and transmission electron microscopy. Scientist Paul and Frizzle in 1992. So this is how the tracks looks like. Okay, so this is the track formation. TEM transfers electromagnetic images of latent induced tracks parallel and perpendicular to view. This is a appetite. Okay, 20 nanometer structure, and you can see 20 nanometer image or of zircon. Okay, so how is tracks formed for this chemical zircon, and this is for aptite. This is view of 20 nanometer, and close view you can see 5 nanometer. How tracks form for aptite and how tracks form for the zircon. Okay, so the track formation, first of all, aptite, as we see before this slide. So this is how the 20 nanometer tracks structure of the aptite, and basically the track diameter reduces along the track, can be subdivided in four sections. Okay, track may be segmented in section 4G. Okay, you can see this. As the particle loses kinetic energy, because you know that once your particle penetrates, so it loses kinetic energy, and nuclear collision increases the deflect and the particle from the straight path. Okay, deflect the path, and because once your particle strikes, it loses the kinetic energy, and definitely it basically deflects the original straight path. Deflect fits with model path, as you can see coming, and this is deflected. You can see somehow deflected, this is coming, and somehow deflected. As you can see, this is coming, and once you're penetrating target depth, means as your depth is going to be increased, you can see the spread of the particles are also spreading, also increase, meaning that more depth basically also your also deflects the particles path, because you can see here is straight, but as the depth increase, you can see it makes a parabolic like shape. Okay, it's now not straight as the depth going to increase. So commonly used mineral phases are these, as I showed you this apatite, and the other is zircon. This is the common used minerals, and these are their phases you can see. And the another new one is the titanate. Their critical temperature is given. And for the apatite, the temperature is 100 to 110 degrees Celsius. For zircon, the critical temperature is 210 to 290 degrees Celsius, and titanate is basically nearly approximately equals to 240 degrees Celsius. Okay, and whereas ppm is part per million, this is the unit of this. Okay, basically we are using uranium and thorium for this concern. Okay, and these are basically the 100 micrometer zoom pictures of apatite, zircon, and titanate. Okay, these are the east tracks in apatite. You can see these are the tracks formed in our track detector. You can see this is the 20 micrometer zoom picture of apatite. Okay, in apatite basically 16 micrometer length and 1 to 6 micrometer width. Understood? And this is basically the 5 micrometer picture. You can see clearly how the tracks formed, and this is again the 5 micrometer picture, how you can see the tracks formed. You can see not clearly in this, but you can see clearly how many tracks basically formed in apatite when with 20 micrometer zoom. So this is the tract, each tract in zircon. Okay, as you know that zircon is another mineral. So this is the 20 micrometer zoom for zircon, how tracks formed in zircon, and this is basically the 5 micrometer picture, and again this is 5 micrometer in zircon, basically about the approximately 20 micrometer in length and 1 micrometer is width. Now move on towards the fission track dating, differences to other radiometric dating methods, and daughter product is a physical damage of the crystal lattice. Okay, so the daughter product is basically the who is responsible for the damage of the crystal lattice. Okay, so which factors basically control the amount of fission track in mineral? So there are, so you can say that which factors basically which controls the amount of fission track dating in minerals. So number of fission tracks increases with time, because with the evolution of time, number of fission tracks also going to increase. Along with that, number of fission tracks is also proportional to the uranium concentration. The more the uranium concentration, the more will be the fission tracks formed. There is a direct relation of uranium concentration with the number of fission tracks. But the fission tracks can anneal and number of fission tracks decrease with annealing. Okay, so as you decrease the annealing, so number of fission tracks can be, you can see that the number tracks can anneal and number of fission tracks decrease with annealing. So the reason is that because fission tracks annealing can leads to complete healing of the crystal defects. So annealing basically is a process in which you are going to basically heal the crystal defects. Also, the healing is mainly depend on temperature. You can also by increase or decrease the temperature to go for annealing. Okay, and annealing is basically for the individual grades. This is basically the fission track dating protocol. There are two principles of dating protocols, and the first principle is the external detector method, which is EDM, and the second method is basically the laser based fission track method, which is LAFT. Okay, so what is external detector method? EDM basically it is for the determination of uranium concentration. Okay, EDM is basically for the determination of uranium concentration, irradiation with the thermal neutron and inducing fission of uranium-235 and counting on an external detector. So for that we are going to use an external detector in external detector method. Okay, so we are going to use an external detector for the counting for the induced fission of uranium-235 and counting on the thermal detector. Okay, and the another method is basically the laser based fission track method, which is so called as LAFT, and this is for the purpose for the determination of uranium with laser ablation. Okay, inductively coupled plasma mass spectrometry LAICP-MS is used. Okay, so this is are the two basically principal protocols of fission track dating. So what is external detector matter in depth? So you can see these are basically the accumulation of spontaneous fission tracks. The upper surface has to be polished, okay, throughout the crystal. Move on towards the spontaneous track east. Now you can see the spontaneous tracks are now east. This is are the surface. These are confined. This track is confined, and then we are going with the external mica detector attached. You can see this is the external mica which we attach on the spontaneous track east. Okay, crystal. Okay. Then what we are going to do after attaching this mica detector, then we are our task is for the thermal neutron irradiation. Okay, thermal neutron irradiation means neutrons. Which neutrons? Slow neutrons have to be applied, not fast neutrons. Okay, induced fission tracks register in detector. So after it register, it induced track is only in detector you can see, and there are two plan of views of several crystals. These are the mirror images you can see. So this is for the grain mount showing spontaneous tracks in the individual grains. And this is the external track mount showing the individual track defining grain outlines. Okay. So this is the same external detector method which I already mentioned you before. Okay, so this is same. Basically, the external detector. This is natural caustic mica free of uranium and impurities. There is free of mica and there is of uranium and there is no impurities. Okay, and impurities. Okay, and the thickness is around about 1 millimeter of this external metal detector. So this is again the same external metal detector. We already discussed the qualifying the number of parent isotope of uranium-238 by counting tracks induced by fission-238 by thermal neutron during irradiation in the nuclear reactor. Okay. Also, the thermal neutrons may be captured by uranium-235. It gets stable and fission into two fragments. Along with that, a large number of fraction of released energy is kinetic energy and is induced fission tracks is formed in grains and on external detector. Similarly, number of induced tracks is depending on uranium-235 and uranium-235 to 238 ratio is constant in nature, which is 1 divided by 137.9. Okay, same. This is the thermal neutron irradiation. After that, induced fission tracks registered. After registering, induced track is only on detector, and there are the two plane mirror images are to be formed. Okay, and this is the same external metal detector method. So basically, it depends upon, as I told mentioned you, that induced track density, which is denoted by rho I for the uranium 235. Okay, where with the cross section this. Now our next is basically the laser-based fission track method. In laser, basically is used to evaluate the counted grain, suffer and measure the uranium-238 concentration with ICP-MS. Okay, and also this method was developed by Scientist Hasibi at in 2020 in 2004. Okay, and this routinely used in many laboratories. This laser-based fission track method is mostly used in many laboratories. Okay, this is how you can see the fission track sample preparation with different crush with jaw crusher. You can see having jaw crusher, Steve less than 300 micrometer, very fine to coarse sand size, and the concentration is heavy minerals with streaking table. Okay, and the SCP from the outer minerals using heavy liquid magnetic techniques and to make the virtually non-magnetic. So these are the visualizations you can imagine. Now these are the fission track sample preparation. Make amount of many apatite or zircon grains less than 100 grain and depolish and etch to reveal the spontaneous track. So we are going to see the reveal the spontaneous track. So for that we are going to use the apatite or zircon grains less than 100 grain and polished and etched to reveal. These are the images. Sufficient drug sample preparation aptite etching is 5.5 molar HNO3 for 20 seconds at 20 degrees Celsius. Similarly, zircon etching in NaOH and KOH solution at 220 degrees Celsius for 6 to 150 hours mean time. And lastly, the zircon etch time depends upon the accumulated radiation damage. This is how you can polishing the apatite and zircon. These are the methods. So that's all for this lecture number 13 of principal methods and applications of nuclear tracks. In next lecture, we are going to continue our discourse. So till then, take care. Allah Hafiz.